Hi everybody, welcome to this recorded session on Douglas bags and the respiratory calculations that are associated with them. So this recorded session is supplementary to the practical that we did last week. So by now you should have done the practical in the labs and you will have collected your expired gases in the Douglas bags. During that session, we recorded heart rate, and then at the end of the test we took down the gas concentrations for percentage O2 and percentage CO2 along with the volume of expired air in each bag. So with that data and along with the lab temperature and barometric pressure, we can then work out what the VO2, VCO2 and RER are for each bag, and then also identify at which point or with which bag maximal oxygen uptake occurred. Okay, so I don't want to dwell on this part too long because I'm sure you've probably seen some of these symbols before within your first year studies, and some of you may have seen them in prior studies before that. But there are a number of different symbols specific to what we're going to be doing in the practical that we'll be looking at. So first of all is P, capital P. And I say capital P because you will see a capitalized P and a lowercase p. They are different, and when we come on to doing the lectures, I'll talk more around what the difference between those capitalized and non-capitalized P's mean. But in respect of this practical, capital P simply refers to pressure, okay, be it pressure of blood or gases. In respect to the Douglas bag practicals, it simply refers to gas pressure. V, generally, again, it tends to be a capital V, relates to gas volume. And then sometimes you'll see a capital V with a dot over the top of it. So that dot simply means it's the value that you're looking at is a function of time. So in this case, gas volume per unit of time or flow. So typically when we're looking at respiratory gases, we tend to measure those gases per minute. Okay, so liters per minute, milliliters per minute, etc. F simply means fractional concentration of gases. Capital I and capital E refer to inspired and expired gases. And these different symbols can be combined in various different ways. So for example, if you saw FiO2, that would be referring to fraction of inspired oxygen. If you saw FeCO2, then that's fraction of expired CO2. Okay, so we can use these with other symbols, O2, CO2, etc. Nitrogen, less so nitrogen because we don't, unless we're in a hyperbaric environment, nitrogen is relatively inert and we don't really need to take any notice of that. But within this session, O2 and CO2 are the key ones that you're going to be looking at. Okay, so symbols used specifically within exercise and metabolism, or exercise and metabolism studies. Kind of alluded to this on the previous slide. You've got VO2, VCO2, RER. They're the three that we're particularly interested in within this practical, or within the practical that you'll be doing to supplement this this presentation. So again, you'll notice that the VO2 and the VCO2 have a dot over the V. That's just indicating that it's a function of time. And again, in this case, we're looking at in either breaths per minute, liters per minute, milliliters per minute, etc. RER refers to respiratory exchange ratio. Sometimes you'll see this referred to as respiratory quotient, or RQ. Okay, they often get used interchangeably. The primary difference being that RQ is recorded in situ within the lungs. So for exercise purposes, exercise testing, obviously that's not practical. So we tend to, as sports scientists, refer to respiratory exchange ratio, RER, okay, because that's done via remote equipment. So in order to calculate RER, it's simply the ratio of carbon dioxide produced to the amount of oxygen consumed, and it's simply VCO2 divided by VO2. In terms of how you actually get that little dot over the top of the V, there's a couple of ways that you can do it. Now, I would suggest going forward, when you're writing your lab reports up and your assignments, you should try to get into the habit of writing V dot rather than just a normal V. Okay, now you're not necessarily going to lose marks on that, so don't stress out too much about it, but we should be now starting to use the correct scientific terminology, correct symbols, abbreviations, etc. So there's three ways in which you can get the V with a dot on. The first one is probably the most long-winded, and I probably wouldn't recommend doing it, but you can go into Word, go into Insert, I think it's the maths function, or equation function, sorry, in there, and you'll see within that there's an option to select the V dot, and there's other different symbols in there, but it's a bit of a faff, so I probably wouldn't do that. Another easier way of doing it is to just simply go online, find a journal that has it in it, and then simply copy and paste and paste that into your Word document. Whilst that's pretty easy to do, the only limitation with that is sometimes when you paste it into your Word document, it can tend to pixelate a little bit or quite a lot, and it can be either quite hard to read, or it can also mess up the formatting around that of your other text. So I'm not saying don't use that. I've done it, and it largely depends. Sometimes it doesn't pixelate and it's perfectly fine. Sometimes it does. It depends on which document you're getting it from. So you can use that if you want. The third way, and probably the easiest and cleanest way to do it, is when you're typing it in your Word document, when you write your V, before you write your O2 or your CO2, type V, and then immediately after it, without a space, type 0307. And then if you press Alt and X together at the same time, and then let go, it'll automatically convert that V to a V with a dot. It's nice and clean, won't pixelate. So, as I say, when you're doing your assignments, just keep that in mind, okay, and trying to get into the habit of doing that V dot. Okay, and lastly, before we get into the calculations themselves, there's three key conditions that you need to take into consideration when you're doing these respiratory calculations. So the first one is referred to ATPS, or ambient temperature and pressure saturated with water vapor. Okay, so this is a value that looks at the pressure and the temperature of air when recorded remotely. So when we're using things like online spirometers, things like that. Okay, but we need to make sure we note the temperature, the ambient temperature, and the pressure of that gas. Okay. The second one is BTPS, and that's body temperature and pressure saturated with water vapor. Okay, so any air that we take in or breathe out will have an element of water vapor in it. Okay, even in really cold weather. That's partly, and again, I'll come onto this a little bit more in the lectures in a few weeks' time. But even in really cold, dry weather, it's impossible to freeze the lungs, because as you draw that cold, dry air in, moisture from the respiratory tract and the lungs will heat that gas up, and it will produce moisture within that gas. Okay, and it's this moisture, this water vapor, that we need to take account of. So BTPS, body temperature and pressure saturated with gas, and that's used when we're measuring lung volumes in situ. Okay, so from within the lungs themselves. Excuse me. And then the third one, arguably the more important one, is STPD, so standard temperature and pressure of dry gas. Okay, so you'll see on the next couple of slides, when we start to go through these calculations, all respiratory gases ultimately need to be expressed in STPD values. Okay, so they need to be converted. So the STPD is simply a conversion measurement that takes into account the ATPS and BTPS water vapor values. So the standard temperature and pressure of a dry gas is 0 degrees, 760 millimeters of mercury. Okay, that is a dry gas at sea level. Okay. Okay then, so hopefully everything is clear up to now. So we'll move on to a worked example. So first of all, let's assume we've collected some values from our Douglas bag. So we've got a gas volume in the Douglas bag of 62.10 litres. Now that's BTPS. Okay, so that's pressure and temperature of gas within the lungs. We've got a fraction of expired O2, so we can see that the FeO2. So going back to the first slide when I said these symbols can be combined. So we've got an FeO2 value of 16.86%. So that's 16.86% oxygen in the expired gas. We've got an FeCO2 of 3.60%. We've got a fraction of inspired oxygen of 20.93 and a fraction of inspired CO2 of 0.03. Now remember, these are inspired volumes, so they shouldn't change. Okay. The only time that they will, well, no, ignore that. I was going to say the only time that they will change is if you're at altitude, but that's a load of rubbish. It'll be barometric pressure, so we ignore that comment. So these inspired gases shouldn't change. It's these expired gases which will change. The other thing that will change is the barometric pressure. Okay, so these are some data that we collected in previous years within the Darwin physiology labs, and at the time of collection the barometric pressure in the lab was 750 millimeters of mercury, so just slightly less than that standard 760, and the lab temperature was 26 degrees. Okay, so when you come to do your lab practicals, all these you'll get these values from using the dry gas meter and the Servomex the Servomex gas analyzer. Okay, and I'll talk you through those when we get into the labs. Okay, so before we can actually calculate ventilation, so this first slide is looking at minute ventilation, and this is a value down here that we get to. The first thing that we need to do is calculate what's called an STPD factor. Okay, and that factor is going to be used to convert this value, this 62.10 litres BTPS, into a STPD value, which is what we see here. Okay, so in order to calculate the STPD factor, that's calculated as 273 divided by 273 plus T. So that 273 is temperature in absolute Kelvin. That's a constant. It doesn't change irrespective of the calculations and these values up here. That will always remain 273. T refers to temperature in the lab. That is multiplied by barometric pressure divided by barometric pressure in the lab, I should clarify, which is this 750, minus pressure of water, and I'll come on to that in a second, divided by ambient barometric pressure, so 760. So again, that 760 is always a constant because that is the barometric pressure at sea level. Okay, so before we do any of this, we need to work out this pressure of H2O. So pretty straightforward, 13.955 minus 0.6584 times temperature plus 0.0419 times by temperature squared. Okay, again, these values are constants. You don't need to worry about those. It's just the temperature values that you need to change. So what I would do first is work these two bits out first. So 0.6584 times by temperature, which is 26, gives you 17.12, and then 0.0419 multiplied by temperature squared, again 26 squared, is 28.32. So overall, you've got 13.955 minus 17.12 plus 28.32. And that gives us a value of 25. Okay, so that is 25.2, sorry. So that is the pressure, okay, of water vapor. So back over here, we work that out. So 273, which we said was a constant, divided by 273 plus temperature. So 273 plus 26 gives you 299. Divided by 750, which is our barometric pressure in the lab, minus our pressure of water vapor, 25.2, divided by standard barometric pressure at sea level, which is 760, which gives us 0.913 multiplied by 0.954, which gives us an STPD value of factor of 0.87. From that, to work out your minute ventilation is pretty straightforward. Just simply take your value in your Douglas bags, your volume should I say, in your Douglas bags, 62.10, and multiply that by your STPD factor, so 0.87, which gives us an end volume, ventilation of 54.03 litres per minute. Okay. Hopefully that wasn't too complicated, okay, and I'll give you another example later on that you can try and work through in your own time and try and do it prior to coming to the first session in the labs. Now, bear in mind you're all at different times, excuse me, so make sure you do check your timetables and you turn up to the correct session. Please don't come to other sessions because your friends are in that session, because we have a limited space in the lab, and obviously social distancing rules are still applying, so we need to limit the number of people in the lab. So please check your timetable and stick to your timetable slot. Okay, so next we're going to calculate VO2, okay, not to be mistaken with VO2 max, okay, that's the highest. When we're looking at the Douglas bags, we're looking at VO2, the volume in the gas bag. Now, it's very difficult to identify VO2 max. Well, I'll say it's difficult to identify VO2 max. That will be your end bag. But in terms of identifying the exact time point where VO2 max occurred is challenging when using Douglas bags, because they're just not that sensitive. Okay, unlike an online gas analyzer like the Metallizer, which we'll show you, or the Cosmed system that we've got in there in the lab, they measure breath by breath, so it's very easy to identify that's where VO2 max occurred. In a Douglas bag, you've only got however long you're collecting gases for, so 60 seconds typically per bag. But that aside, we're going to measure VO2 on this slide, or calculate VO2 on this side. So again, it's in STPD values. As I said before, all values have to be converted to STPD. Values up here that we've recorded from that bag are the same, but this time you'll notice N2, okay, so nitrogen values are involved. Now, the first thing to say is we don't directly measure nitrogen, okay. We calculate it simply from the fact that when we're measuring gases, we're only measuring oxygen and CO2 in those expired in the Douglas bags, so in the expired air. So in order to determine what expired nitrogen is, you simply take 100%, take away whatever percentage of oxygen, take away whatever percentage of CO2 you've got. So in this case, 16.86 and 3.60, and then whatever's left, whatever percentage is left, that's your nitrogen, your expired nitrogen concentration. Inspired nitrogen concentration is the same, it remains the same, 79.54%. So to calculate VO2 is VE multiplied by fraction of expired nitrogen divided by fraction of inspired nitrogen, multiplied by a fraction of inspired oxygen, and then minus the fraction of expired oxygen. Okay, so think back to your school days and your maths. Work out what is inside the brackets first. Okay, don't try and do it all sequentially because you'll end up with the wrong calculation. Work what's in the brackets first. So we know that VE is 54.03 litres per minute because we just calculated it on the last slide. So work out this bit first. So fraction of expired nitrogen. So if we take these percentages up here, 16.84 and 3.60 away from 100%, excuse me, that leaves us with 0.7954, okay, as a fraction, so 79.54%, okay. Divide that by the inspired nitrogen concentration, so 0.7904, multiplied by inspired O2, so it's 20.93%, so as a fraction 0.2093. Work that bit out first, excuse me, which gives you 0.2106, and then minus your fraction of expired oxygen, so 0.1686, so simply move your decimal place 2 places that way, which gives us 54.03 multiplied by 0.042, okay, which results in a VO2 of 2.27 litres per minute, okay, as STPD values. Okay, apologies if my camera down here is blocking this little box, okay, but all it's saying is this is in absolute values, okay, so litres per minute is in absolute oxygen uptake. If you want to convert that to relative values, so millilitres per kilogram per minute, then you simply take that value, divide it by body mass and multiply by 1,000, okay. So reason why we would do that, it helps to scale our O2 values, our VO2 values for different individuals, taking into account different body mass. It's not perfect, okay, and some larger individuals, so if we're thinking in a sports context, people like goalkeepers. Apologies for that, folks. April just popped into the office. Okay, so where was it? Yeah, so some athletes like goalkeepers in football or rugby players, particularly large rugby players, may be penalised a little bit by this millilitres per kilogram per minute value, okay, as much as it tries to scale it relative to body mass as much as possible. As I say, it's not perfect. Another way to do it is what we call allometric scaling. So you would take this millilitres per kilogram value and then raise it to a power of 0.67. That is a more accurate way to compare values across individuals, yet to my knowledge it's rarely ever done. Okay, when you're looking at sports science journals and the different articles in the, very rarely will you actually see authors use allometric scaling. Why that is, I don't know, apart from the fact that it's just a little bit more of a faff to do. So just bear that in mind. If you ever do see any values which have a little point superscript 0.67 next to it, that's simply meaning that they have done that allometric scaling. Okay, I hope you're still with me, folks. It does get easier, trust me. This is the last slide of calculations, and as you'll see as we go through these different calculations, always start in the same order. Always do minute ventilation VE first, then your VO2, then your VCO2, and lastly your RER. Okay, and they do get sequentially easier as you go through those calculations. Okay, and if you get stuck, don't worry about it. As I say, we'll be going through all this in the practical, and hopefully it'll make a little bit more sense when you get into the labs. Okay, and I will go through it again with you then. So last slide then. Okay, VCO2, so volume of carbon dioxide. Again, STPD. VCO2 equals VE multiplied by a fraction of expired CO2 minus the fraction of inspired CO2. Dead easy, this one. So we know V is 54.03. Fraction of expired CO2, well, we know the percentage is 3.60%. So again, just move your decimal place So that gives us 0.036 minus fraction of inspired gases. Well, we know that inspired percentage is 0.03. So again, just move your decimal place 2 places. So that gives us 0.0003. So 54.03 multiplied by that is 1.93 litres per minute. Again, that's an absolute value. Okay, so 1.93 litres per minute of carbon dioxide were produced during this particular stage of the test. Okay, I probably should have said at the start, the values for these that I'm using were taken from an incremental ramp test on the treadmill. Okay, I can't remember what stage during the test this was, but looking at the values, I would say that it was probably relatively early on to mid stage. So remember, VO2 was around just over 2 litres per minute, so not particularly high. And then lastly, we've got respiratory exchange ratio, RER, which is simply VCO2 divided by VO2. So 1.93 divided by 2.27. So yeah, just over 2 litres per minute, which gives us an RER value of 0.85. Okay, so what does that 0.85 tell us? Okay, I'll go into more detail on this again within the lectures on respiratory physiology. But an RER value of 0.85 tells us that at a particular time point during that test, they were using a mix of carbohydrates and fats. Okay, so the lower that RER value, the more it indicates you're burning predominantly fats. Mid-80s is mixed fuel substrates, so fats and carbohydrates, and then above I think it's 0.9, I think, excuse me, is burning exclusively carbohydrates. Okay, and then once we get up to 1.15, that is indicating that you are working more anaerobic. Now, I should say, careful of the term there, more anaerobic. It means you're supplementing aerobic metabolism with anaerobic metabolism to a greater extent. There's not this big switch over. Okay, and you may have been taught in first year or your A-level studies, whatever you've done before, that you get to a certain point and you start working anaerobically. Okay, there's not this big switch over from aerobic to anaerobic. You just start to supplement aerobic metabolism to a greater extent with anaerobic metabolism as well. Okay, so if you see an RER value of 1.15 or greater, that would indicate you're starting to supplement to a greater extent with anaerobic metabolism. However, that value, and this value here as well, is largely influenced by what you eat and when you eat it. So whenever we're doing any of these tests, and bear this in mind for when you're doing your practical in the labs, ideally you want to refrain from eating and drinking for a couple of hours prior to testing. So for those of you who are willing to volunteer to do the actual testing and get on the treadmills, if I could ask you to try and not eat for at least 2, ideally 3 hours before you come to the session. Okay, that's easier for those people who are doing it in the morning, scheduled 9 till whatever. Just don't have breakfast. Okay, easy. For those later in the day, it becomes a little bit more challenging. Have a breakfast and then maybe don't eat your dinner until afterwards. Okay, because otherwise, if you eat something and then rock up to the lab straight afterwards, these RER values are going to be all over the place. Okay. Okay, so there you have a completed worked example of how to calculate the different parameters using Douglas bags. So hopefully you didn't find it too challenging. I think the key thing to remember is just making sure you get your brackets in the correct places. One suggestion might be to go and refresh yourself with BODMAS. You may have covered that many years ago in school, but that'll help you to determine where you put those brackets and which bits you should work out first. The only other thing to add is here's another worked example, so I would like you to have a go at this in your own time. The only difference here is I'd like to convert the absolute values to relative values, so you'll need the body mass. So in this case it's 69 kilos. Now the answers are on the next slide, but please try to have a go at this yourself before just skipping straight to the answers. Alternatively, you can use the data that you collected yourselves in the lab sessions, and again you'll just need your participants' body mass to be able to work out the relative values. But if you've got any questions or you're unsure on any elements that I've gone through in this session, then just either send me an email and I'll get back, or grab me at the end of one of the lectures. Thank you.